Okay, so our robot is mainly focused around the cubes, which I guess is kind of a given that's the main piece this year. But we really wanted to be able to get up to the scale when it's all the way at its full height. We thought that would be pretty important because we were a little worried that once a team got possession of the scale in the middle, it would be really hard to get it back since it gets so much higher. So we were really designing on being able to get the cubes up high enough to put them onto the scale when it's at its max height. We had climbing as our lowest priority because we figured, given the fact that there's a levitate, if you're able to manipulate the cubes, then you can get the same effect as if you have the climber. So while we did focus on it, it was our lowest priority. We were mainly really just focused on getting the cubes up that high. So for our robot, we didn't really want to spend our 3 days focusing on a drivetrain because we figured we had a better use of our time on the other subsystems. So we went with just a pretty standard 4-sim, single-speed, 6 Coulson drivetrains, like a tank drive. We have 3 4-inch Coulsons on each side. The only significant part about this drivetrain is the fact that we have a cutout in the front, which is important for getting the cubes far enough into the robot to be able to manipulate them properly, because we didn't have an over-the-bumper intake. We did have a bit of a design oversight. We realized after the competition, or after the 3 days was over, that we're really not sure if we can get up onto the platform by the scale. We just completely forgot about it, to be honest. So we're not sure if this would work properly or not for that element of it. But the rest of that, we were focused more on getting speed so we could zip around the field rather than pushing, which is the only kind of real thought we put into this drivetrain before just slapping it together to focus on the rest of the bot. So for our intake, something that a lot of the experienced people on our team have learned over the years is that easy intakes for the driver are really, really important. So like a good lesson for that is 11.14 in 2015. It was really, really, really easy to get the game elements into the robot. So we wanted to focus on that. The main way we're going to try to do that is have something that just flips over the bumper with some spinning wheels to just suck the crates, or suck the cubes into the robot. Given our time constraints and our part constraints, we actually weren't able to do that, which we were pretty disappointed about. So we mainly focused on, once the crate is in the robot, how we're going to manipulate it. From there, we had 3 main design ideas. One was to use these squishy compliant wheels to clamp onto the crate, using the same spinning wheel idea as before. Another one was to use pneumatics or something else to clamp onto the cube sideways. And the third idea we had was similar to in 2014, just a bar that flips down over the top and has rollers to suck the crates in from above. We decided to start prototyping all of them because we figured that the best way to validate a design is to actually test it, right? But as soon as we had this first one done, as soon as we had our compliant wheels done, we were so happy with the results, we actually just rolled with that and didn't test the others. I mean, I wouldn't recommend that. If you have the time, test everything. You never know what you're going to find. But given our time constraints, once we had something that worked, we just rolled with it. You can see we have the 2 wheels at the bottom here are powered by 775s. The 2 on the back are completely passive. They're just there to give the crate a little bit more rigidity once it's in the robot. I'm just going to enable really quick and show you guys how this works. So both these wheels spin in and just suck the crate in. So you can see it sucks in pretty well. We use this exact same mechanism to then eject the cubes afterwards. So either at a low position around here or actually up above the robot for the scale. We have enough height to eject these cubes at both heights. And we just run the same wheels in reverse and just shoot them back out. And it's gone out of frame. So that's pretty reliable. We can get a decent amount of distance throwing the cubes. And the last thing I'm just going to show you guys is that we played around a lot with the compression on these wheels to find the best way to get a reliable, sturdy grip on the cubes. So if we suck it in here, you can see that even when we lift the arm up, like these are holding the cube very securely. The cube's not tilting or wobbling around. So just using these 4 compliant wheels, we were able to get a very, very sturdy grip on the cube, and we're actually really happy with the result there. For our lifting mechanism, that was what we thought would be the most important mechanism for this robot, because we really, really wanted to be able to get the cubes up onto the scale when the scale was at its max height, which is difficult considering the fact that your robot has to start constrained in the height, and then it can go unlimited afterwards. So to keep it constrained but get that same height, we had a couple different ideas. First, we were thinking maybe an elevator would be a good way to go, but some of the people on our team had bad experiences with elevators in the past. We thought about a cascading elevator, but that just adds even more complexity to the problem. We thought about a 4-bar, but ultimately we decided to go with an arm because the arm, well, actually we went with the arm because it was simple, really. And because after a little bit of CAD, we validated the fact that the arm would be able to hit all those heights while also keeping it very simple. So like I said, we made a 2D CAD of the arm, which is really, really important to figure out the geometry of this arm. We really had no idea at first whether this arm would be feasible to go from the ground up to the, 6.5 feet that we need to get the cubes onto the scale at the top height. We had no idea if that was possible to fit within the 60 inches here and hit all those heights. But after validating in CAD, we realized that it was going to be achievable. The main way that this does this is we actually get the arm all the way over past the top of the robot and shoot the cubes out backwards to get that extra little bit of height, but it all works out perfectly. So this arm can hit the switch, the scale, and can pick up off the ground, which is exactly what we wanted. For our climber mechanism, this was our least important mechanism, and so we worked on it last. We were trying to take advantage of mechanisms we already had built on the robot, so we didn't want to build a whole deploying system for the hook. So we designed it into our arm. You can see here that this is our hook. It's a little bit sketch. It's all held together by Velcro, but it actually works quite well. So we have our one spool at the bottom of the robot, which has a rope running all the way over top of the arm and to this hook, and the hook is held in place with Velcro. As we run the spool for the winch, it breaks the Velcro and flips the hook over onto the bar. From there, we just keep running it, and it pulls off of even more Velcro. It might fall around to the ground, but I'm going to give it a shot. You can see it comes right off of the top, it pulls off the Velcro, and the hook comes off of the top and will hook onto the bar, and then we'll winch the robot up like that. So we took advantage of just using some simple passive parts like Velcro, so that we don't need to build a whole mechanism to deploy the hook. And then we just have a simple 775 Pro on a 100-to-1 reduction gearbox as our spool. And the robot, it works pretty well. There's some videos of us climbing with this simple setup. It's pretty cool how we managed to get this all done passively. I think it's just a good testament to our build captain and the creativity that he had.